Welcome to the mind of a math teacher.
Hey, it is a beautiful day to learn about some derivatives of exponential functions. So here we go. I've got three goals for this lesson for you. The first one is that we want to be able to find the derivative of e to the x, the exponential function, or using base e, also known as Euler's number, about 2.718 as the base of this exponent. And because that happens a lot in nature with exponential growth, it's a really good thing to understand, really a proof of why the exponential function is its own derivative. It's a really neat result. The second thing that we're going to look at is the derivative of any other base to the x. So imagine if you had 2 to the x, or 5 to the x, or 17 to the x, any of those, then we would get this rule, and we're going to show that that's the case. The derivative of a to the x is ln of a, the natural log of a, times that original function a to the x. And that only happens, of course, when a is greater than 0, because we would have a very strange jumping up and down, back and forth situation if we did a negative number to the x. And then we'll finish off with a bunch of examples. I have 6 examples for you of using these rules once we've proven them. So let's dive in to proving our first goal up there. The derivative of e to the x is e to the x. So what we are going to need for this first proof is what I call the limit formula for derivatives, right up here. It's f prime of x, the derivative of the f function, is the limit as h approaches 0 of f of x plus h minus f of x all over h. And that just comes from finding the slope and letting that slope, the limit as h approaches 0 of that slope idea, rise over run. If you'd like a video reviewing how that works, I can do that for you. Just put a comment in the description below. And our second thing is we need to have this limit already known to us. So the limit as h approaches 0 of e to the h minus 1 over h is just going to be 1. And that is a fundamental limit that you should already know if you're trying to approach this topic. If you don't, we're going to use it in this proof. But again, you can leave a comment, and I would love to go through really explaining in depth why that limit is what it is, and I can help you out with that. So let's get started with our proof with those two things in mind. First, we want to just say the limit as, or I'm sorry, we want to just say that f prime of x is going to be the limit as h approaches 0 of e to the x plus h minus e to the x all over h. Nice. Now, this can pretty easily be handled with just understanding our exponent laws. If I rewrite limit as h approaches 0 real quick, we can do a plus. E to the x plus h is the same as e to the x times e to the h. So now we have this result. And hopefully you can see how both of the terms on the top of this fraction have an e to the x. So now I'm just going to factor out the e to the x, and I'll have e to the h minus 1 left over on the top, like this. And since this e to the x is multiplied and there are no h's involved in that whole e to the x, I can bring that outside of the limit, and I have e to the x times the limit as h approaches 0 of e to the h minus 1 over h. So then all I need to do is recognize this limit as what I mentioned back here. Okay, so that limit is 1, which means we get e to the x times 1, which is, of course, just e to the x. So what we've ended up with is, starting with our function being e to the x, we have the derivative of our function is also e to the x. It's a very interesting function that is its own derivative. It is its own rate of change. And that's why natural things tend to grow at this rate, or a rate similar to this. It's because as things grow, the amount that they're going to continue growing is really dependent on how much of the thing you currently have. If you think about bacteria growth or population growth, that's the way that it works. Now, let's go to the next level, where instead of having this very, very special number e at the bottom, we're going to look at having any other number as your base to your exponent. So what we need to look at for this one is we're going to try to take the derivative of a to the x, where a is greater than 0. So a could be any positive number. It could be 1/2, it could be 85, it could be 1,000, 1,000 to the x. And there's a little bit of a trick to this. And also we're going to use the chain rule. So those are the two things that we need. We need this little trick and we need the chain rule. Now let's talk about the trick first, because really it's just a little bit of algebraic manipulation. It's not really a trick. The idea is right up here. A to the x is going to be the same thing as e to the x ln a. And I just want to prove that to you really quickly, that those are exactly the same thing, because we're going to replace our a to the x with e to the x ln a, and I want you to be comfortable with doing that substitution. So here we go. We want to try to prove that this is true. And so in order to do that, we can just look at rearranging this to kind of write it as a logarithmic expression. So what I like to do is say this up here is the exponent on e that gives me a to the x. I'm going to say that one more time and underline it in blue to make sure that you can really see this. This is the exponent on e that will give me a to the x. And as I say that rule for how you can read an exponential and turn it into a logarithm, I'll just rewrite it. This is the exponent on e that gives me a to the x, right? The exponent on e is just ln, natural log. And so I have x times ln a is equal to ln of a to the x. Well, this is just the power rule for natural logs, right? That we could bring the x out to the front, or we could bring it back up as a power. We know this to be true, so this up here must be true. So that's really nice. That's a nice result. We can substitute for our a to the x right here at the beginning with e to the x ln a. So that's what we're going to do. So now we've got the derivative of e to the x ln a. Now, that might look worse, but it's actually a lot better, because we already know how to do the derivative of e to a power, right? It's just e to that power, right? The derivative of e to the x is e to the x. So now all we're going to need to do is the chain rule. I like to say that the chain rule is just the derivative of the outside function leaving the inside function alone times the derivative of the inside. So here's what that's going to look like. If I do the derivative of the outside function here, leaving the inside function alone, well, the outside function is just e to a power, right? E to some power is the outside function that's happening here. So I'm going to continue to have e to that power, right? The derivative of the outside function, the derivative of e to a power, is just e to that power. So I've left the inside alone, and I've just done the derivative of the outside function, leaving the inside alone. Now we want to do times the derivative of the inside function. Well, the inside function is just ln of a times x. And ln of a is just a number. So really we have this number times x. This is a linear function, so its derivative is just going to be the number that's out in the front. So we just get ln of a. Now we have our derivative, but it doesn't look very good. It's not in a really nice form. And all we need to do is remember from back in the beginning, e to the x ln a was up here. It is just a to the x. So this becomes ln of a times a to the x. And we've got exactly what we were trying to prove. QED. Quite easily done. All right, now we're going to jump into using these rules in examples so that you can get a feel for noticing how that works. So we're going to start with simpler examples, and we'll move into ones that are a little bit more complicated. But we're just going to use the rules. We're not going to go all the way back to the fundamentals each time of doing the limit formula for derivatives. We're going to use the rules for these derivatives that we've already proven and build upon what we've already done. So our derivative here is similar to what we had just looked at in using the chain rule. So we can say, well, the derivative of the outside function is just e to the negative 2x. It's just derivative of the outside, leaving that inside alone, times the derivative of the inside function. And what is the derivative of negative 2x? Well, it's just negative 2. And we're all done. So that's nice. All right, example number 2. In a similar way, hopefully you can see how this is not that big of a stretch. So I would recommend pausing the video and seeing if you can take the derivative of this, and then look at my result after you're done. Okay, you're back. Let's see how you did. We would want again to do the chain rule, derivative of the outside function, leaving the inside alone, times the derivative of the inside. And we have our result. How did you do? All right, let's move on. Now this is going to start putting together multiple rules as we move forward. When you want to take the derivative of two things added together, you can of course just take the derivative of the first term and then add the derivative of the second term. So let's do that. Similar to our previous example, we might start jumping ahead here and getting our results a little bit faster. You've started to notice a pattern in how this works, and hopefully you could say the derivative of e to the 7x is just going to be 7e to the 7x. And for our other derivative, we'll have 8e to the 8x. Again, using the chain rule, but this time we've started to develop some intuition for it so that we can work through it a little more quickly. Let's look at example 4. All right, now, there's a little bit of a situation here because we've got to start bringing in our derivative of a to the x when we see this 4 to the x term. So I'm going to write that rule down for us so that we remember it from before. The derivative of a to the x is ln of a times a to the x. That way we have it as a little reference on this page. So here's how we want to do our derivative. Notice first I have 5 times something, right? That's really an outside function happening here. I could use the product rule, but that's going to be clunky and it's going to take extra time. So I'd rather use the chain rule for this. And picture it's just like the derivative of 5y with respect to y. Well, that would just be 5 times the derivative of the inside. Our inside here being 4 to the x. And we'll get the derivative of the inside is ln of 4 times 4 to the x. Cool. Now, on the other end, we're going to have minus 9 e to the negative 9x. Ask yourself if you understand how I got that and how the chain rule for this term worked out just like examples 2 and 3. So there is our result. Example 5. All right. Now this one has two different a to the x situations, and we're going to have to slow ourselves down and make sure that we're really working this out well. We also have a negative out in the front here and a negative 9 in the front right there to really be considerate of. So if we look at the negative 6 to the x term first, the way the derivative is going to work is I can look at it like it's a negative 1. So I'm just going to replace this right here with a negative 1 times 6 to the x. And then it's really similar to what we had just looked at. So let me actually erase this so that you can see my negative 1 a lot better. Here, let's get this looking good for you. We have negative 1 times 6 to the x. Okay, nice. So now we can think about it with the chain rule like we just did. This is negative 1 times something. Well, the derivative of negative 1 times something is just negative 1. But I'm doing the chain rule, so I need to do times the derivative of the inside function. Well, the derivative of the inside function, because a here is 6, and we have 6 to the x, we'll have ln of 6 times 6 to the x. Cool. Now, on our other term, we should get negative 9 would be the derivative of the outermost function, if we look at it like negative 9y with respect to y. And then we'll have to do times the derivative of the inside function, ln of 5 times 5 to the x. And there is our result. So make sure you're being careful about these numbers out in front and that you're really thinking through how the chain rule applies in these situations. All right, our last example, the most complex one that we could come up with. And let's go through this. So we have 6 times something, 6 times e to the negative 4x. Okay, 6 times anything, the derivative is just going to be 6. But then I can do times the derivative of the inside, which is, as we saw before, negative 4 e to the negative 4x. That's again using the chain rule, where we did the derivative of this outside function, leaving the inside alone, times the derivative of the inside, which is just this negative 4 out here. All right, and in a similar way, these other ones are going to work out just like that. So we'll have plus 8 times negative 3 e to the negative 3x, and we'll have plus 2 times negative 8 e to the negative 8x. I almost ran out of room there. Okay, now that's a really long expression that will need some simplifying to happen. So what we really have here at the beginning is negative 24 e to the negative 4x. And then for our next term, we also have negative 24. But this time it's e to the negative 3x. And then last we have minus 16 e to the negative 8x. And that is all set. Now, I wouldn't mind these negative exponents here because we're looking at exponential functions. And since those negative exponents are not the same as each other, we can't combine these terms together in a clever way. We'll just have to stop there. So, if you like this video, it helps me out. It helps it get in front of more people. I think that's the way YouTube works. If you comment on this video, then that helps you because it will show me what other videos you'd like me to make, things that you'd like me to answer and help you understand. And if you subscribe, it also helps you because then you'll get these videos much faster. You'll get them as soon as they upload and you'll be notified of that. So have a great day and keep on learning.